Okay, we're going to talk about forces in circular motion, and really we're going to be talking about uniform circular motion uh, because we want to have circular motion right now at a constant speed. And so you can imagine this is the top view of a ball or a disc or something that's spinning around that's being swung around in a circle on a string. It's moving in a horizontal circle, and it's being forced to do so by a string. We know that any object moving in a circle has an acceleration towards the center, which we call the centripetal acceleration, which is v squared divided by the radius, right? And so this object is accelerating in that direction. And in terms of the forces in the plane of the table, in the plane that we're looking at, the only force acting is the tension, and it's the thing that's producing this acceleration. If we were to cut this rope somewhere, we would see that the disc would just go off in the direction in which it was headed, rather than continue to follow around the circle. It's the tension from the rope that causes the ball or disc to move around in a circle. So this is, we might call this the top view. And now we'll look at a side view. And just for simplicity's sake, we'll say this thing is sitting on a horizontal table. Let me try that again. That's a little better, right? And so I'll go get my yellow string here, and I'll say, here's the center of my motion. I'm swinging it around from this point somehow, and and here is my mass. We'll say it's like a hockey puck or something, so it looks square from this direction, from the horizontal direction. So now we're looking from this way, right? We're seeing the view from this direction, and now we can see that there's also a normal force, right? And then a weight, right? And here's the tension going this way, and the acceleration direction is this way. And this almost looks like a free body diagram now. I've identified all my forces. I haven't quite put them all on a dot. If I was going to redraw this as a free body diagram, I would just let me try that one again. Right, I would put my normal force here. I would put my tension this way. I would put my weight this way. And then I would identify my acceleration direction, and I would identify my coordinate system. Right, and this gives me a picture of the details of what's going on. The only force acting in the horizontal direction is the tension, and it's the thing that's causing the object to accelerate towards the center. And this acceleration is the centripetal acceleration we've talked about before. And so any object moving in a circle has to have some force causing it to accelerate towards the center. Often we will call that force the centripetal force, but it can have lots of sources. In this problem, the centripetal force is the tension. But if we were talking about a planet, the centripetal force would be, say, gravity. When you're on a car going around a clover leaf on a highway, when you're driving a circular path on the highway, the force of the centripetal force is the friction force. And so when we say centripetal force, that doesn't really identify the source of the problem. It just says that there is a force that's causing the object to move in a circle, and we haven't said what it is yet. So this is what our free body diagram looks like, just from the previous screen. Here's the tension, right? And it's the thing that's driving the object to move in a circle. It's the only force acting in the x direction. And so if we take our free body diagram and we write down the sum of the forces, we get the sum of the forces in the x direction equals ma sub x. That's just our centripetal acceleration. I could call it a sub c if I wanted to, right? And that's just m times v squared over r, because the centripetal acceleration for an object in uniform motion is just v squared over r. And then I can get a very simple expression for the sum of the forces in the y direction, since the y direction is coming out of is vertical to the plane of rotation, there's no acceleration that way. And so I just get the normal force and the weight are equal, right? And so that tells me what the normal force is. But then if I look at the x direction, right, if I go back and look at my x direction, the only force acting in the x direction is the tension, and left out an m here, it's the tension is equal to the mass times the centripetal acceleration, which is equal to the mass times v squared over r. And so I get the tension in the rope is equal to the mass of the object times v squared divided by r. It's just the mass times the acceleration of the object. Notice that if I want to double the speed of the object, it takes 4 times as much tension, right? Or if I want to halve the radius, right, it takes twice as much tension. For two objects moving at the same speed, the one that with the shorter radius is accelerating at a greater rate and therefore needs a greater tension. Similarly, if I go to a slower velocity, right, it requires less tension. And so the tension goes as the square of the velocity and inversely proportional to the radius. So for another circular motion problem, we now have a car traveling with constant speed v on a circular horizontal curve, say just around the clover leaf coming off the highway or something, of radius r. And so what's the minimum value of the coefficient of static friction that will keep the car on the road? And so we can say a few things here. First of all, we recognize that the car is traveling with velocity v tangent to the circle at any time. This is our car. And we know that the acceleration at any time, we can call it a sub c. Let me clean that up just a little. I want to make it pretty horizontal, right? A sub c is just v squared over r. That's the acceleration of the car, and it's towards the center of the circle always, so it's this way. I was leaving a little room back in here so I could show that, one more time, that the force of static friction is the thing that's pushing it to the right in this picture. This is a top view of the scene. And so we're looking down on the car. Gravity is pushing into the screen and the normal force is pushing out of the screen. Some force has to be pushing the car towards the center, and it ends up being the static friction force. We can draw a front view over here if we just want to call it the front view. Right, and I can just draw a little road here and maybe get a blue for my car, right? And here's my car, right? And so the car is coming at you. There are its wheels, right? Here's the top of the car, right? So if we wanted to talk about all this, so here its headlights, right? It's coming towards you, and so we know that there's a force of gravity this way, and that there's a normal force going that way, and that there's a friction force going this way as the car goes around the curve. Now you can tell that there's some force acting there, because if the road was slick, the car would slide off the road. The car way over here would keep going in the forward direction if there was ice. Once again, the acceleration is this way. A sub c is v squared over r. And so if we wanted to draw a free body diagram, say down here, we could just draw our forces here. Here's our normal force. Here's the force of friction. Here is the force of gravity. Again, the centripetal acceleration is this way. And so it'd be pretty straightforward to come up with a coordinate system for this, right, which would look like that. Just the standard coordinate system we have. And so on our next screen, we can just solve this problem. We can say, look, the sum of the forces in the x direction equals ma sub x, and that's equal to ma sub c, and that's equal to mv squared over r. Similarly, the sum of the forces in the y direction now just add up to 0, because the car isn't moving off the road or into the road. It's just it's staying motionless in the y direction. And so all of its motion is, all of its acceleration is towards the center. Notice we don't have to worry about the forward or backward direction because it's traveling at a constant velocity that way. All right, so we'll continue this on the next screen. So once again, here's here's the free body diagram for my car. My car is just the dot, and it's accelerating to the right. The car is coming at you, as shown on the previous screen. There's a normal force acting up and a force of gravity acting down, and the force of static friction is pushing the car to the right as it comes towards you, and that's producing this acceleration that's v squared over r. And so I can just come over here and I can say, look, the sum of the forces in the x direction equals ma sub x, and that's just ma sub c, which is the centripetal acceleration, which is mv squared over r. And so the static friction, the force in the x direction is just F sub s, and so this just says F sub s is equal to mass times v squared over r, except the static friction force is also equal to mu sub s times the normal force. The reason we use this equal sign instead of the less than or equal sign, which comes from the definition of the static friction force, is because we're saying it asked us to choose the minimum value of the static friction force that will keep the car on the road, and that means the static friction is just getting ready to slip, which means the static friction force is at its maximum possible value. And so then we can write this equation this way. We could say, well, mu sub s times the normal force is equal to mv squared divided by r. And then we have to come down here and look at the sum of the forces in the y direction equals 0. Well, let's just say equals ma sub y, and that's equal to 0. And so that just says the normal force minus the weight is equal to 0, or the normal force is equal to the force of gravity, which is equal to mg. And so now we can substitute this, right, into here, into the normal force, and we get, we can come down here and we get mu sub s times mg is equal to mv squared over r, or mu sub s is equal to v squared over rg. And so if the car is traveling with velocity v and the curve has radius r, the minimum value of the coefficient of static friction that will keep the car on the road is v squared over rg. You could phrase the problem differently, and you could say, what's the fastest a car could go and stay on the road for a given static friction? You would just solve this for v is equal to mu sub s rg, or you would say v is equal to the square root of mu sub s times r times g. And what that's saying is that for a given value of the static friction and a given radius of the curvature of the road, this is the maximum value you can have and still stay on the road. Those two ways of answering that question are kind of similar. So let's just put some numbers to that previous example. Suppose the car is traveling at 30 meters per second and the radius of the highway is 50 meters. What's the minimum value of the coefficient of friction, static friction, that keeps the car on the road? Again, our formula for that was mu sub s is equal to v squared over rg, and so we can just solve this. We can say this is 30 meters per second squared divided by 50 meters times 10 meters per second squared. And so this is, 900 meters squared per second squared divided by 500 meters squared over second squared. Right, and so this is 1.8. That would be a pretty high coefficient of static friction. Nevertheless, that's what would be needed to make a turn that tight at that highest speed. So now we're going to look at a slightly different problem. One way that cars stay on the road is by the coefficient of static friction, like we saw in the previous example. But now we're going to look at a problem where the tilt in the highway keeps the car on the road. You may notice that sometimes when you're driving around the highway, turns are tilted. And so the idea in this problem is to address how the tilt in the car relates to the maximum speed it can have without sliding off the road. And so in this problem, we see a car is rounding a frictionless curve. So for the sake of this discussion, we're going to say there's no friction, and the road is banked at an angle theta, right? And the question is, what is the maximum speed the car can have without sliding off the road? And so now we're just relying on the tilt in the road, even though the problem looks the same as it did before. This force that's keeping the car on the road is no longer the force of friction. It's the force from the road acting on the car. And so let me just draw a little picture of this here. So just as before, I'm going to give you a front view of this, right? And we're going to have the car coming at us, except this time the road is, I'll draw less tilt than that. Maybe I'll draw it like this, except a straighter line. Well, we'll go with that one. And so here's my car, right? And here's the tilt in my road. Oops, I got to put in a horizontal line here. Right, that's horizontal. This is the way that my highway is tilted. And so once again, I can draw my car here, right? Let me try again on that. Not the best car in the world, but okay. And there are its wheels, right? And then here's the body of the car, right? And there are the headlights. And here's the driver, right? And you notice that now the normal force is off to an angle this time, right? And so if I draw the forces acting on this car, I would say gravity is acting this way, right? This is the force of gravity. But now I have a normal force that's going off this way, right? I have no friction force, and so ask yourself, you should pause this occasionally and ask yourself, are there any other forces acting on this car? The answer is no. Let's look at a few other questions. What's the direction of acceleration for this car? Can you answer that before I tell you? So again, you might think about just pausing here and seeing if you can figure out what that is. Since I'm going to tell you now, since it's a flat circle, the road is tilted. The angle of the road is tilted, but the road is flat in terms of the direction of the circle, and so the acceleration is actually towards the center of the circle, which is this way. So this is like somebody going around a banked curve on a flat highway. The road itself isn't horizontal, but the circle is horizontal. The road is tilted. And so that's the direction of the acceleration. So I can draw a free body diagram for this thing now. Let me just pick a different color for that, just for fun. And I'll just draw it down here. Here is my object. There's my normal force, right? Here's my weight, right? My acceleration is this way. There we go. So here's my force of gravity, and here is I keep trying to get it right, there's a horizontal acceleration. It's v squared over r, right? And this is telling us how to pick our coordinate system, right? And you might think just because we've been doing ramps that you want to have your coordinate system going down the ramp, but that's not true in this problem. We want our coordinate system so that the acceleration is along an axis, and so we're going to pick an acceleration this way. And so first I would ask you, which of the vectors in my force diagram am I going to be finding components for? And the second question I would ask is, what force is responsible for this centripetal acceleration? That is to say, what in this case is our centripetal force? And so to answer that, you should try to answer that on your own. But let me pull in a different color here. So what I do is I draw my coordinate system on here, right, like this, and like this, right, and I'm going to pick another color. I'll pick orange, right? If the force that gets broken up is the normal force, as you might be able to tell, and so I guess I'm keeping the same color, and so there is the normal force, and if I come back down here and look at the angle of my road, right, this angle here is the thing I'm calling theta, right? And that means this angle here is 90 minus theta. And since this is 90 degrees, that is to say the normal force is perpendicular to the road, that means this angle here is theta again, because this angle with 1 hash is the complement of this angle, which is 2 hashes, which is the complement of this angle, which is 1 half. So that means this theta down here is the same as that theta up there. And so now I have a normal force in the x direction and a normal force in the y direction. And I can say Fnx is equal to Fn times sine theta, and Fny is equal to Fn cosine theta. And it's the Fn sine theta, it's the x component of the normal force, that provides that centripetal acceleration. And as long as the road's tilted, that normal force, the horizontal component of that normal force, can help push my car around the curve. And so what we're doing in this example is we're saying, hey, suppose the road was super icy. If the road is tilted by a certain angle theta, how fast can I go around that curve? So we'll finish this on the next page. So I've redrawn my free body diagram here, and I broke the normal force up into components, Fnx and Fny, from the previous screen. And so you can see this becomes a fairly straightforward problem. I already wrote down the definitions, but I'll rewrite them again. Fnx is equal to Fn sine theta, and Fny is equal to Fn cosine theta. And so we can see that I can now just plug in, and I can say, look, the sum of the forces in the x direction is equal to ma sub x. That's equal to ma sub c, which is mv squared over r, and then I can say the sum of the forces in the y direction equals ma sub y, and once again that's equal to 0, because we have no motion in the y direction. The car is just going around the circle in the horizontal plane. And so since I have the y here, I'll just go ahead and finish that out, right? The forces in the y direction say Fny minus Fg is equal to 0, or Fny is equal to the force of gravity, or Fn cosine theta is equal to mg, right? And then if I go to the x equations, I get the sum of the forces in the x direction equals mv squared over r, but that just gives me the normal force times sine theta is equal to mv squared over r. And now I can use this expression, right, and solve for the normal force. I can say the normal force here is equal to mg over cosine theta. And that allows me to substitute in here, and so I can say mg over cosine theta, where I've taken this quantity that I'm going to circle here, right, and substituted in for the normal force here, times sine theta is equal to mv squared over r. And now my m's cancel, right? Sine over cosine is tangent, and so I can say, I can either solve for the angle or the velocity. I can say the maximum speed, I can say v squared is equal to rg tan theta, or v is equal to the square root of rg tan theta, right? And so that's the maximum speed a car can make around a turn of radius r and angle theta that has zero friction. Now usually there's some friction even on an icy day, and so in principle you could do a little better than that, but this would at least tell you, given an angle on a road, what speed you should ride on if it's got absolutely no friction at all, and you could still make it around the curve just fine. So I'll just, on the next screen, I'll just work out just a quick example. So let's just do an example in which we pick the radius of the road to be 100 meters, and the tilt angle is 15 degrees. And so we say, what is the velocity, the maximum velocity that allows us to get around that curve? And so that just gives us v is equal to the square root of 100 meters times 10 meters per second squared times the tangent of 15 degrees. And I get that to be the square root of 268 meters squared per second squared. And that gives me a speed of 16.4 meters per second. So that's how fast a car can go around that curve in the absence of friction if the radius of the curve is 100 meters. Obviously, if you double the radius of the curve, you've got less curvature, and so you're going to be able to have a larger velocity, right? Similarly, if you tilt the angle up higher, if you make it a steeper angle, you can go faster and still not fall off the road.